Hello everyone. I wanted to talk about atomic structure and especially electron configuration as it relates to atomic structure. So back in honors, we did talk about how an atom is put together, about how the protons and neutrons are in the nucleus, the electrons are flying around or somehow occupy space around the nucleus. So the mass of the atom is we're really in the nucleus, and the space of the atom, the three-dimensional space it takes up, is really this thing called the electron cloud. But again, when we talk about the electron cloud, we are talking about something that is a little bit strange, almost like we really don't know what it really is. So we have several different models that we've come up with, and we have some now agreed on what's called the quantum mechanical model. Okay, the quantum model. So anyway, just for FYI, all electrons have a combination of what are called four quantum numbers. They're actually not numbers; they're actually letters. And the four quantum numbers says that every electron has its own home address around the nucleus. That is not necessary for us to know, okay? But we do have to put this together in a way that is functional for us to know how electrons exist around the nucleus. So essentially we have seven large spaces around the nucleus called energy levels, and that's represented by the letter N. Inside those energy levels, we have what are called sublevels, and inside the sublevels, we finally find orbitals, which is probably the place where we'll find an electron. And notice I use the word probably. So probably is, of course, there's a probability, a higher probability that we'll find an electron in a certain place. Okay, electrons are very elusive, though, and we'll talk about that in class. It's very difficult to find them. So again, these are areas where they probably exist. And of course, as you can see, there's 2 electrons for every orbital. Okay, these are what the orbitals, what they think they look like according to the quantum mechanical model. So you notice here's just a single s orbital. Here's 3 p orbitals. Here's 5 d orbitals. And down here, you'll see there are 7 total f orbitals. So 1, 3, 5, 7. Okay. Now I know you've seen this before, so we'll go through that pretty quickly. But 2 rules really that we need to follow when we do what are called electron configurations. It's called the Pauli exclusion principle, where no 2 electrons can have the same set of quantum numbers. And the second thing is that electrons will occupy the lowest orbital that can receive it. In other words, they'll kind of snuggle in closely to the nucleus, okay, to start. Okay, so as far as energy levels goes, we know that those are the big spaces or the big places that electrons probably exist. And the first energy level has the lowest energy, the second has the next highest, third, so forth, all the way down to the 7th energy level, which is not only the highest energy, but also furthest away from the nucleus. So we can picture the nucleus would be about here, and everything else would be in. Now, here's the thing, I'm drawing it as concentric circles. It's really not that way, but we'll go with that, okay? It's very difficult to describe how it would be otherwise without you knowing quantum mechanics, at least a deeper version of quantum mechanics, okay? Now, the sublevels work the same way. Sublevels, S is closest or has the lowest energy, so if here's the nucleus, energy level 1 has a 1s, and then it gets a little bit more complicated from there. So now we've got to assemble the energy levels and sublevels together, and that's where our discussion is going to come from. So every energy level has a certain amount of sublevels. Energy level 1 has 1 sublevel, S. Energy level 2 has 2 sublevels, S and P. Energy level 3 has 3, S, P, and D. 4 has 4, 5 has 4, 6 has 4, and all the way down to 7 having 4. So notice they keep repeating SPDF, SPDF, SPDF. Okay? Now, each sublevel has a certain number of orbitals. So notice I keep getting smaller. Energy levels to sublevels to number of orbitals. So now S has 1 orbital. P has 3, D has 5, F has 7. We've already seen those numbers about 3 or 4 slides ago with those funky balloon shapes, okay? And if every orbital contains 2 electrons, as it says down below on that slide, then we see this. The maximum number of electrons that S can hold is 2. The maximum number that the P sublevel can hold is 6. The maximum that the D sublevel can hold is 10. And the maximum that the F sublevel can hold is 14. Okay, so 2, 6, 10, 14, because all I did was multiply all these numbers by 2 because we have 2 electrons per orbital. Okay, so those are the maximum. So you can have less than. Here's how the periodic table is set up. Here in this pinkish color here, or whatever this is all the S block. Okay, so notice 2 electrons, 2 columns. Okay, then let's jump over here to this green thing. This green thing here is the p orbital, the p block, excuse me, 1, 2, 3, 4, 5, 6. 6 columns. Ironically, there are 6, that you can hold a maximum of 6 valence electrons, or 6 electrons in the p block. D has, guess how many? 10. There we are on the D block, so there's 10 all the way here. 10 total, or 10 maximum electrons can fit in the D block. And then the F block, we're not going to worry about so much just yet. If that comes across, we'll definitely worry about that in a second, okay? So what we're going to do is, let's do some electron configuration. What we're going to do is follow the periodic table. We're going to read it like a book, okay? So essentially what we're going to do is, let's keep playing off of this slide right here. Let me erase everything. Okay, so with this slide right here, I want to get to oxygen, and oxygen's right here, okay? So oxygen's right there, and what we need to do is start counting, okay? Whereas this is actually hydrogen. This actually should be over here a little bit. So anyway, if we start off with the 1s, now it gets a little funny here because the 1s and the 2s are separated to start. So actually, this could be over here or this could be over here. It doesn't matter. But again, it starts off a little rocky. So 1s2, okay? 1s2. So let's write that in. And then now once we're done with that, we're at the end of the first energy level. So let's go to the second energy level. So down here, we're now going to read here. Now I'm in the S block, so 2s2, 2s1, I'm sorry, 2s1, 2s2. So that's filled. So now we got to jump over to the P block, all the way over here. So now I'm going to jump all the way over here, and now I have P1, P2, P3, P4. So that's in the fourth column of the P, it shouldn't be 6, but that's the fourth column of the P block. So now I have 2P4. Now I tend to not write the 2 again, okay? All right, so I tend to write 1s2, 2s2P4, and that's the electron configuration for oxygen, okay? So I know that it has 8 electrons, so 2 plus 2 plus 4 is equal to 8. It has 8 valence, it has 8 total electrons. I didn't identify that already, okay? So let's jump to chlorine and let me see if I can fix my mistakes. So let's get rid of all this stuff here. And let's go to chlorine. Chlorine would be right here. It's element 17, so there's 17 electrons. 17 electrons in that atom that I have to draw. So sometimes I make a note when they start getting a little larger, okay? So if I read across the periodic table, again, it always starts with 1s2, 2s2p6. Let me show you where I got those. So here's 1s2, done. 2s2, 2p6, okay? Now I'm down to here to 3s2. Notice I just keep reading the block. I'm in the S block here, so that's 3s2, 3s2. Now I'm still in the third energy level, so I tend not to repeat my 3. Jump over to here. 3, and I know I said it, but I won't write it. 3p1, p2, p3, p4, p5. 3p5. So I'm still in the third energy level, so I'll just write p5. Let's see, 2 plus 2 plus 6 plus 2 plus 5 is 17. Okay? So that's electron configurations. Let's try strontium. It's a little larger. Okay? So strontium, we have this. Let's see, strontium is element 38. Okay, so it's a little larger now. So we're going to have to incorporate the D block. D block is always one behind the period that I'm on. I have a rule for that coming up here. Okay? So as far as strontium goes, starts off the same, 1s2, 2s2p6. So again, I'm just trying to name everything behind it. So here's the 1s2, done. 2s2, 2p6, that's all filled. 3s2, 3p6, okay? 3s2, 3p6, so 3s2, p6. And notice I'm still in the third energy level, so I don't rewrite the 3. Okay, now it gets a little funky. So let's go down here. So now I'm in 4s2, but I'm trying to get all the way down here, okay? So with 4s2, let's write 4s2. But now I mentioned D is always one behind, and there's this funky overlapping I'll explain in class. Actually, it's coming up on the next slide. But this overlapping is tough to predict. But once you get the hang of it, it is very predictable. So I know that if I take the period that I'm on and subtract 1, that's the value of the D block. Okay, that's the value of the D block. For example, if I go here, so I'm here. So now look, it says 3D. 3D. So I'm in the D block, so it's 4 minus 1 is 3. So 3D10, because it's totally filled. I'm filling the whole thing here. 3D10. So let's go back here to 3D10, but I'm still not done. So now I'm back to 4. Okay, now I'll explain that in a second. So I'm back to 4. So that's completely filled. 4P6, still not done. So let's keep going here to this. Now, you'll notice that I went back to 4. So it turns out that S and the P block are equal to the period that you're on. S slash the P block are equal to the period that you're on. So if I'm on the 4th period, it's 4S and 4P, but it's 3D because it's one behind. So now I'm down to the 5th row. I'm just trying to get here, so it's 5S2. And when you add up all these electrons, you should end up with element 38. Okay, 38 electrons. Okay? Okay, let's try one. I will write the answer, and you guys just check your work, okay? So pause when you need to. All right, let's go to cobalt. Okay, so if you want to pause, go ahead, because I'm going to write this out. Done. So 2 plus 2 is 6 is 10, 14. That should be 20. Oops. Oh, yeah. Okay, we're good. Okay. 1D2, 38. Sorry. I had to keep checking my math. Okay, so anyway, that's that. All right, so that's electron configuration as far as that goes. Now, this is the reason why there's all this weird overlapping. You notice that energy level increases here. So this whole arrow increases. As I move up, here's all my S's. Here's all my P's, D's, and F's. But you notice that the P's keep lagging behind, and then the D's come in. Okay, so at 1S is first, 2S, 2P, 3S, 3P. Then you expect D, but D has a higher energy than S. So S actually comes before first. And this is because there's overlapping, and I'll explain more of that in class. But again, the overlapping is the tough part. Okay? Once you get the hang of it and you understand the rules, and these are the rules, S and P is equal to the period number, D is equal to the period number minus 1, and F is the period number minus 2. Okay? Once you keep those in mind, it actually makes it quite easier. So trying one more, let's go to, let's see if you guys can do indium, element 49. Okay, make a little note, element 49. So pause when you need to. It's 1s2, 2s2p6, 3s2p6, 4s2, 3d10, 4p6, 5s2, 4d10, finally 5p1. 5p1. Okay, that's the final answer. So that's 10, 10, 10, 10, and 9. Element 49. 10 plus 10 plus 10 plus 10 plus 9 is 49. Okay, just to check. I also ended in the first row of the P block, and I'll explain that in class in case you forget. Okay? Sorry for the longness of the video, but you can try these on your own if you want. I will post the answers here. Actually, we'll go over these in class. We've done enough for now. Ions. Ions are simple. This one's gained 2. This one's lost 3. This one's gained 1. This is lost 2. So oxygen would look like this. But it's gained 2. So its oxygen is 1s2, 2s2p6. Notice that's the same thing as neon. This is the reason for that. Look at aluminum. Lost 3. So Al looks like this. P6, 3s2p1. Okay? But it lost 3. So eliminate these three. Look at that. That's the same as neon, the same as oxide ion. So oxide ion aluminum look the same. And there's something called the noble gas configuration. Chloride, of course, has gained one. That'll end in, just so you know, that'll end in 3s2p6. Iron, ooh, that's different. Okay, so let's talk about iron. We're going to lose one of these from the highest occupied energy level. Okay, you lose them from the highest occupied energy level first. So it's 1s2, 2s2p6, 3s2p6, 4s2, 3d5. Okay, let me just make sure that that's 5. 1, 2, 3, 4, oh, 6. I'm sorry, 3d6. Excuse me. Okay, now the rule is that you lose electrons because it's lost 2. You lose them from the highest occupied energy level first. That's the highest occupied energy level. 3 is not as big as 4. So let's not worry about 3. You're going to lose them here first. Okay? So your final configuration for the iron 2 ion is 1s2, 2s2p6, 3s2p6, 3d6. Done. Okay? That's that ion. Okay. The rules I have for that are somewhere. Here we go. We'll talk about this a little bit more in class, but that's essentially what we're doing. When you have cations, electrons are always lost from the highest occupied energy level first. Okay, I think I make a big point of that. Okay, I just did that with the iron and the iron 2. We'll talk about that more in class. The video is getting a little long for now. And we'll talk about orbital rotation in our next video. Email me with questions.